It's perfect. Okay,
Go for it.
so you can begin. Thank you very much.
Okay. So um, first, thank you all for coming back. It's truly wonderful knowing that there are so many masochists in the community. Um, for the whole time we've been discussing everything from symbiotics and cataclysmics and planetaries and H2 regions and supernovae. The one thing that has always been lurking in the background and that never gets mentioned because it seems almost pornographic to do it are magnetic fields. There's a wonderful comment from uh, Van der Hulst from the 1970s that's a joke, but it's very true that um, magnetic fields are to astrophysics as sex is to psychology. That's almost it's almost a truism depending on which area you're in, because it serves both ways, that we both invoke magnetic fields and ignore magnetic fields. So let me start with why we can't ignore them. And to do that, we really have to go back to the beginning of the business. That is, when astrophysics became a subject in its own right, that in the 1890s, when Hale and his contemporaries were propagandizing for spectroscopy and the link to the laboratory, as opposed to celestial mechanics and dynamics, when the Astrophysical Journal was founded and the Italian Society of Spectroscopists was founded, when Tacchini and Secchi were doing classification, Hale had the ingenious idea of looking at the sun, which isn't exactly an ingenious idea, but because of the connection that has historically been sitting in the background for almost 40 years at the time he came up with the observation, it was known that there was some kind of connection between activity on the sun and magnetism on the Earth. Now, this goes back to the Carrington event of 1859, that what we now understand to have been a massive coronal mass ejection triggered not only incredibly intense auroral activity in the northern hemisphere, but it was also registered in magnetic observatories. Now, again, I hope you'll tolerate a little bit of the history. Um, as always, please, if it's getting to be too much, just stop me, okay? The the discovery that the magnetic field actually has a structure, and more to the point that it's not stationary, goes back to the middle of the 18th century. First, with the first maps of the distribution of magnetic orientations, that is, declination and orientation, azimuth, which was thought to be a way of creating a navigational chart. So you could use the magnetic field as a coordinate system instead of celestial because it was fixed on the Earth. But when it was also realized that there was a change in the magnetic latitude as a function of time, mainly as observed in England, And the whole concept of electromagnetism and induced magnetism started to filter through the physics community. The idea that you could actually set up a coordinated set of observatories that would measure the magnetic field and the sky was championed by several, among whom was Gauss and Weber, and this became one of the major projects of the 19th century. And that's why it was possible with the Carrington event to link this to an astronomical source, because these observatories were identical and coordinated all over the Northern Hemisphere. Many of them later were also associated with timekeeping. So you had the astrometry and the geodetics being done at the same place. The reason for mentioning this is that by the end of the century, the other thing that had been discovered by Schwabe was the sunspot cycle, that what had already been noted, the variation of both the sizes and the distributions of the spots, was also linked to an actual variation in the structure over time, both in the sunspot number and also in their location. And so by the end of that century, there was some idea that maybe the sun was somehow influencing the magnetic field of the Earth, and if not just the field, also maybe the atmosphere. In the 1880s, Zeeman discovered something that had been conjectured for a long time, that because electromagnetism said light was a combination of electrical and magnetic phenomena, it was not impossible to think that a magnetic field might have an effect on matter. It was already known from the application of magnetic fields to metals that you could polarize metals. For example, the Kerr effect, which is a reflection effect that induces polarization. But Zeeman discovered something rather spectacular that you all know, that if you put a magnetic field across a gas that's emitting or absorbing, you suddenly see multiple lines, and the separation between the components, which are as unique to the lines as the lines are to the elements, depends only on the magnetic field strength, but that depending on the orientation of the observer, and this is what's peculiar, if you look either transversely or parallel to the field, you see different effects. Okay? This was a clue to atomic structure. It led to Lorenz's theory of the electron. In fact, it's usually targeted now by historians as the real discovery of the electron, even more perhaps than Thomson's measurement of the charge to mass ratio. But the thing that's important about it is that exactly in the way that spectroscopy had been shown to be a tool by Kirchhoff and Bunsen and Fraunhofer and all of the work on the morphology of spectra and the identification of the elements, now you had a tool for actually understanding something about the environment itself. You could see if the magnetic field was present or not just by looking at the spectrum. And in fact, it didn't require anything spectacular. When Hale first did the observation, it was purely resolution. It had nothing to do with any specific spectropolarimetric instrument or anything else. In fact, here, let's just go to one example. I'll change screens here. Okay, can you see this?
Yes.
Okay, this is
Yeah.
a high resolution spectrum taken at National Solar Observatory. It's a near infrared spectrum. It doesn't matter which line it is. You see there are multiple lines here, and they're broadened by different amounts. This is the slit. So it's a long slit spectrum across an active region that's only about a few arc seconds across. And yet, across this region, you can see projected along the slit that there's clearly a difference in the magnetic field structure without any special instrumentation. This is what is so remarkable, I think, about the beginnings of the study of the sun as a magnetic object. But this is also the realization that you have an interaction between the magnetic field of the sun and the surface structure of the sun. You see, you see these lines. In this case, this happens to be an iron 1 transition, but that's not important. What is important is it's present along the whole slit. The, Essentially, the spectrum itself is not variable. The line strengths are variable, and their widths are variable, but overall, the surface composition isn't different. Even the major changes in temperature or pressure aren't all that different. This is mainly the magnetic field. And the other is that the magnetic field that you were measuring in these regions, which could be compared with laboratory measurements. Again, this was as important as understanding that you could identify elements on stars like the sun based on samples in the laboratory. See, what you're seeing here can be calibrated without knowing a damn thing about atomic structure, in the same way that you can identify elements and ions in 19th and early 20th century papers without knowing what the structure of an atom is. You simply make the strong assertion that what you see in the laboratory is replicated in the cosmos. So the fact that these lines were present and that they were split meant you could measure the field in an absolute way. Okay? This is fundamentally different than many of the other measurements that are available to you. You don't have to calibrate the spectrum in absolute units, except for wavelength. This is what's remarkable about this. The fact that you have a linear detector, of course, helps, because then you can also compare the intensities. But it is enough to know the splitting, to know what the field is. Now, there's a very important caveat to what I just said, and it goes back to this statement that the orientation of the observer makes a difference. So if we go to, let me go to a different screen now and hope that it will show up. Okay, so the concept is the following. If we take as our model atom a two-level atom, same thing we've been doing from the beginning of our discussions. And for want of a better name, we will call the lower one AEL and the upper one EU. Okay? Now, as we don't need to know in detail what the classification is of any one of these levels, the fact is that this starts out from some configuration of the electrons. And I realize this is getting technical, but I hope this will be okay. That all you start with when you're building an atom is how many electrons do you have? I mean, let's forget about crap of orbits or anything like that. The individual electrons occupy not an energy, but a configuration. Okay, it's the number of people who are coming into the auditorium. You have different ways of placing them on their seats, depending on their tickets and which seats can be occupied. And each one of those has a different energy and a different configuration. Okay, suppose all of them sit in the front row. Then you're in the ground state. But if a few of them happen to be in, say, the first row, and then you've got a couple in the second row, that's a different energy. And yet it's the same electrons. So the point is you're redistributing them. That's called coupling. So whether you have a particular coupling scheme of one or another kind, you'll still get energy levels and you will still get the transitions between those. And the only thing you need to know is that every time you see a transition between these levels, that transition corresponds to an energy difference. Okay? Now, the discovery of the Zeeman effect said that when you put a magnetic field across the system, you take this level and, if it is possible, separate it into sublevels. The quantum mechanics here is the statement that you have a magnetic here. You see the arrow. Think of the arrow as being a magnetic moment. And so you have the arrow here and the field here, sorry, here. And the field can be aligned or it can be anti-aligned. And those have different energies. Okay? So far?
Yes.
If you increase the field strength, the separation increases. That's the concept of a perturbation. And it doesn't even have to be the same for the upper and lower levels. They can be depending on the configuration of the electrons. Again, think of think of that auditorium. Okay, so here are the seats, and you have people who are sitting here, and then a few of them here, and a couple of them here, and that's one of your configurations. Now, imagine that you have a magnetic field that lifts these guys up, and these guys a little bit less, and these a little bit less. So the energy of the system, instead of being weighted down here, is now higher. Okay, you haven't reordered the electrons. You've simply changed the separation of the seats. Okay? So that separation is approximately proportional. I'll use the symbol B for the field strength because Maxwell did. We've been using it ever since. That the greater the magnetic field, the greater the separation. In exactly the way that you have with the unperturbed atomic states, there are rules that say which of these transitions are possible. So one state going like this and another state going like this may produce a set of lines that look like this, where this is the wavelength. And the separation here between these lines depends only on the magnetic field in your direction. So if you have the atom emitting and you have a field here and the observer is looking in this direction, you measure this field projected along the line of sight, which is called the longitudinal field. So the longitudinal Zeeman effect. Okay, that's what Hale was measuring. But he also was measuring a transverse effect. In fact, he was measuring the total field in the original measurements because it had no polarization. That's a detail that at the moment is to be delayed. The thing that's important here is that the presence of the field. So to go back to the sunspot, is that showing up now?
No, we're seeing your sketch.
Okay. It the anomaly here of yeah. Unfortunately, the anomaly
Yeah.
of uh, Zoom is that you can't easily move between screens. So the other thing that is clear here is that the spots are dark. Um, we take that for granted, right? Sunspots are a skin problem for the sun, but the fact that they're dark is actually not only important, but it's vital for understanding the physics of what goes on in the solar envelope. And so that's the next thing I want to come back to, that here you know that you have a magnetic field. What's more to the point, the magnetic field is clearly a function of the position. Where the spot is darkest, you have the strongest field. This is not an accident. There must be, in other words, an interaction between the magnetic field and the gas in which it is embedded, because what you're measuring here is not a field in vacuum or the field that you would measure with a compass. You're measuring the effect of the magnetic field on the gas that is embedded within it and emitting or absorbing. That implies that the regions that are dark are not emitting at the same temperature as you are seeing in the rest of the photosphere. That the reason for the spot, the existence of this spot, is because the magnetic field structure has been changed and that there's a feedback between the structure of the solar atmosphere and the magnetic field. There's no more fundamental statement that I can make than that, because in the case of the generation of the field, which is the next thing I'm going to get to, we can't look inside the sun. We can't follow the magnetic field inward. Within the photosphere, we're stuck. The only ways we have are remarkably indirect. So the second thing that Hale found was that during the solar cycle, since the cycle is one that begins at one latitude and drifts downward toward the equator. It's not that a single, excuse me, it's not that a single spot here. Let me change screens for a moment. Okay, so when we're talking about the solar cycle, it's that we have regions in high latitude at the beginning of the cycle and regions mainly at low latitude at the end of the cycle. It isn't that these are um, like logs on a river that somehow drift with the river. It's where they appear, that principally at the beginning of the solar cycle, you find the first spots after you go through a sunspot minimum appearing at sort of mid and high latitudes, not at the poles. but at sort of remember that the sun is a differential rotator. So the period at the equator is different than the period at higher latitude. And consequently, the rate at which these move over the field of view depends on where you are. So don't think that this transport is the same as this, okay? The activity center moves toward the equator and then a new cycle begins. And this is the so-called 11-year solar sunspot cycle. What Hale also found was that there was a difference between the leading spot in this rotation and the trailing spot that, and this is very important, this has a sign. The field can be pointing toward you or away from you. And so the separation between the lines can produce either a positive magnetic field, namely delta lambda being less than zero, or a negative field, which is delta lambda greater than zero. Okay, so the symmetry of the line changes. What Hale found was that the leading spot in a pair, that they were always bipolar. That's not obvious from the solar spectrum I was showing you, but that's only one active region and it's very complex. But when you could identify a leading and a trailing, then you saw that the polarity changed. That in one cycle it would be north leading, in another cycle it would be south leading, north and south being arbitrary, simply different. Between those two, and the fact that the field strength and orientation were both changing over time, it meant that somehow the magnetic field was not only appearing and decaying, but it was reappearing. This is the beginning of the concept of the solar dynamo. That while you could imagine the Earth, for example, having a permanent magnet in the center, that somebody has built this enormous electromagnet and keeps it going somehow by paying the bills. The sun doesn't do that. It wasn't realized until the 20th century that the magnetic field of the Earth does the same thing, just on a different time scale and measured differently. But the thing that was dramatic about the sun was that this happened on such a short time scale that relative to any evolutionary time scale you could imagine, the variation of the solar field is on human timescales. Within one generation of Galileo, there had already been a minimum registered in the total sunspot number. I'm going to have to take care of a dog for a few minutes, so um, I hope I'll be forgiven that. Uh, I'll be back in about 10 minutes, so take a pause.
Okay,
I'm
make a little pause.
um yes, so I've also paused the recording. Okay?
Okay. Well, I don't know how long it will take.
So I will take a pause or so.
Well, see that, yeah. We are now at the end of the first season. The next meeting will be about active galactic nuclei. Fantastic subject and also a subject observations in spectroscopy, even by amateurs. And after we shall have a stop for the holidays in July and August, and I think that we will propose a new season, in fact, from next September. So if you have subjects or questions and so on, do not hesitate to send them. And we'll try to organize the agenda for next year, 2025, 2026.
Yeah, sounds good, Francois.
Mm.
Look forward to it. This is very interesting about magnetism.
Yeah. And this is, I think, really a very complex subject. I remember for those who know it, the book of Agnès Ecker. This is a French astronomer working essentially on planetary nebula. She's professor at University of the city Strasbourg in the east of France, and she wrote several books for his students and so on. And I remember I have not eat there. I remember some cartoon explaining the various subjects of astronomy, astrophysics, and so on. And there were a very small part in which he said the combination of mechanics of the fluids and so on becomes very complex when we input the magnetism in the study. So I hope that we will have this night some, I would say, of course, explanations by Steve, but this is, I think, a very complex subject.
Well, I have a question. Is magnetism common to all celestial objects, whether it's galaxies, planets? It's the same effect. Surely it's the same thing. It's a common element.
Yes, in fact, for my very low knowledge, many astronomical objects have a magnetic field at very various levels. And for some of them, this is very important. In the field that I know a little bit, cataclysmic variables, the magnetic field of the white dwarf has a very important consequence. In if the magnetic field is low, you have the formation of an accretion disk. If the magnetic field is high, you have no possibility of the formation of an accretion disk because the material, ionized matter from the donor star, follow the lines of the magnetic field, and the matter accretes on the white dwarf only in the polar regions. So you have no magnetic field, accretion disk, but you have a very strong input of matter at a very high speed, and so very high energy released by the impact of the matter at the surface of the white dwarf. This is called polar, and they are very active and very variables. One of the best of one, and the white one is AM Hercules.
Okay.
Yes. So,
Thank you. Steve is back.
yes,
Welcome.
thank you. Ricky was a little bit faster than I was afraid. So, um, no, that what you're talking about, Francois, is something that is actually directly related to what I was saying about the Carrington. So I guess we should start the recording again.
Yes, of course. This was just an interlude, like in the TV 50 years ago when there was failures. I am the little Twain. So you can go on. Thank you. Please, yes,
Yes, so it's not important that what you're getting is a particular form of the spectrum. It's that you're seeing the difference between the North and South Pole by the asymmetry of the line profile. So the magnetogram has black being one polarity and white being the other. And so this large organized structure that you're seeing is what's referred to as a bipolar active region. You see that there's one pole on the leading side and a different pole on the trailing side. That's what I was talking about before. When they're complex, like here, you can't tell which is leading and trailing. But what you can do is see that the magnetic field directly connects to the structure of the corona, which means the magnetic field that's generated in the sun and regenerated in the sun is also controlling the structure of the outer atmosphere and, just as importantly, is controlling the mass loss. So the outflow here is the analog of what Francois was talking about. Any field, any material from outside falling into the sun is going to be following these field lines, some of which are exceedingly complex. Now, the reason it's so complex here is because the sun is actually losing mass. But if we simply had these loop structures stationary over the active regions, then anything falling in from the outside would be trapped within these regions. Now, this is the solar surface yesterday, taken in continuum light from Solar Dynamics Observatory, which is an orbiting solar satellite. This is taken in visible continuum, and you can see the presence here of sunspots. This is instead the magnetic image of exactly the same structure. Okay? That's so this and this, damn, excuse me. One comes to hate certain brands of computers very easily. So this is again the surface, and this is the magnetic image of the same surface. So wherever you see one of those dark regions, it's clear that it's connected with one of these very strong concentrated fields. But the other thing that I want you to notice, which you couldn't quite tell from that spectrum that I was showing, is that this is the difference between two states of polarization, two circular polarizations. So where it's white, that's not noise. This is not speckle or a signal to noise problem. Every pixel here has sufficient photons that this is actually the structure of the magnetic field of the sun. Look at it very carefully, because this is what the surface of a star actually looks like.
Steve, is this the iron line or sodium or?
Now, this one's an iron line,
Okay.
but with the sun, to do the photosphere, one uses neutral lines or singly ionized metals. The choice of metals is the choice of which transition actually is sort of an optimization of signal to noise, resolution, the optics of the telescope, that also the complexity of the line. You want something with a simple Zeeman pattern. I'll get to why in just a minute, but typically one uses the iron peak. Although you could also be working with say silicon 2 or magnesium 2. Magnesium and calcium are also connected directly as resonance transitions, especially calcium. And so you've got the problem with the calcium of the emission from the chromosphere. But if you do the polarization, that is, you can use the calcium line in emission in the same way that you would use another line in absorption. It's simply formed over a very large range of densities and temperatures, so the interpretation of the field is much more complicated. If you have a weak line, so that it's just formed in the photosphere, then you can be sure that the magnetic field you're measuring is actually the local surface magnetic field of the sun. This uh, this will give you an example. Hoping that I can, oh, yes, okay. Um, this is an image of the sun on the same day. Okay, this is yesterday, except this is taken in the far ultraviolet at 131 angstroms. So this is iron 10. Sorry, iron 20. Not something you're going to find in symbiotics. It's a forbidden line. It's a resonance line. And it's characteristic of gas at a temperature of about 1,000,000 degrees if we were talking about collisional ionization, which is the corona. And so what you're seeing in this is the gas in the corona that's above the active regions whose magnetic fields you were seeing before. Okay? Now, you could measure the Zeeman effect in this too. Of course, you don't, because you don't have that kind of resolution. This is an image and not a spectrum. But in principle, if you measured the magnetic field in this line, you would be getting the field in the solar corona and in the transition region. If you measured the Zeeman pattern of calcium, of ionized calcium, you'd get the chromosphere. And so you could map out in depth the magnetic field of the sun and also the structures. Okay?
Yeah.
This is even more interesting. This is not noise. This is carbon-4, which is tracing gas that's only a couple of 100,000 degrees. It's not the active regions. I should say it's not the corona. This is the chromosphere. And you see all of those little speckles here? Every one of those speckles corresponds to a slightly enhanced magnetic field. This is what's called the chromospheric network. In other words, the chromosphere is actually structured by the magnetic field of the photosphere, even on the scale of a few thousand kilometers. I want that to sink in, because when we measure the surface of a star, you're integrating over all this. In fact, you could do this. I think you're getting my point. You get this to be small enough, and bingo, you get the mean field integrated over that whole surface. That's all you're going to be able to measure in something like this. Unless, as in white dwarfs or some of the other more extreme cases, you have a field that allows you to see the rotation. In which case, and here, if you have these large active regions, as those go by, because the star is rotating, you're going to see more contribution or less contribution from those regions. So let me go back here.
Steve, question before you go.
Please.
So is there material clumping along these places where the magnetic field is stronger?
Yes, there are differences both in the density and the temperature. The differences in the temperature are more extreme, but because you have pressure balance across these regions, there are also differences in the density. In fact, to go as an example to demonstrate that, one has to look not at the static result, but at the dynamical result. This is one example, if I can get the image up here. Okay, so here. I apologize for the awkwardness, but here, if we go to the QuickTime player, this is the 304 angstrom line, so this is partly helium-2. This is the transition region at the base of the corona, and taken from space. So this is from Solar Orbiter. This is a dynamical image. You can see the time here starts at 1610. That was a flare. And you see the you see the material falling back. There is a real density variation. And actually all of what you're seeing in this is not just temperature. This is actually material that's moving along the field lines. So there's a flare. This is what in a DME, a flare star occurs not on a region so localized, but a region that's very much larger. Okay?
Steve, just sorry to interrupt you. When the material is flowing backwards, is that because the magnetic field has started to collapse?
No, it's because the material's cooling.
As simple as that. Not because it's not
the equivalent of a rain. And in fact, this is referred to that way, that the field has partly collapsed, but what's mostly involved is the support for the column of gas that has been heated now drains back to the surface. I think you can see that better in this. Can you see this other solar orbiter film? Or you're only seeing the gray one?
the grey one.
Let's change screens. Okay. Now?
Yes.
Okay, I can't drag this one because of the way that the film was made, but this is a rotation sequence from last year, from a few years ago, taken with Solar Orbiter. So there are the arcs that are connecting the field. This is the higher resolution that you can obtain. And one has to be a little bit patient to see all of the subtle changes here. But if we're a little bit less patient, you can see even here. This is what I was talking about with the chromospheric network. Let's go back one moment. You see these little bright spots that are popping up all over the place? Those are called microflares or nanoflares. That's the evidence. You can see it here. That yes, the densities are also changing. Yes, the magnetic field structure is also changing. Okay, enough of that. So now to go back to here, our images. So the next step is to make direct use of this ability of the Zeeman effect to measure a local field. I hope I can get the whiteboard started. I may not be able to. Since I can't easily get that started, I'll simply explain it by waving my hands and using something else. That if you have the field on a star that's rotating, then so let's use this and imagine that we have these as the two poles, okay? Now, when this is rotating relative to you, at this point, you're seeing one pole, and then at some time later, you may see the other pole. Okay? So if you're taking a spectrum, this would give you a displacement in, say, the positive B direction, and then sometime later, it would be in the negative B direction. Okay? Now, all that would appear to be is a field that's flipping like that to that. This doesn't tell you anything about what the orientation in the field is on different portions of the surface. But remember, you were looking at that image of the sun. So you know that on part of the surface, you have here, I'm being primitive. So here you have a spot.
That's okay.
Okay? Now, in time, because of the rotation, this spot is going to move from being an approaching to receding relative to you. You guys all know this. That's called the Doppler effect. Okay? So you have a localized region on the surface that now isn't just changing its orientation, it's also changing its velocity. And different lines are going to form in different places on the surface because of the difference in the temperature. So looking at, say, the iron 2 versus barium 1 versus calcium 2, you'll be able to map which region is located where by what its velocity changes are. This is referred to as Doppler tomography. It's exactly the same thing we were talking about with measuring the magnetic fields on rotating systems like binaries. The great advantage of this is that because this can repeat, you have a chance to look at the variation over the surface that maps most closely to the spectrum that you see. In other words, you can do the inversion that would be identical to tomography when you're looking with a single beam through a person, but you're letting the beam rotate or the person rotate if you want to make them sick. So you either have the beam doing this or you have the person doing this. Okay? It's exactly the same technique, except people don't have Doppler shifts and stars do. The advantage of this, which is referred to as Zeeman Doppler imaging, actually goes back to 1948 and a paper by Armin Deutsch, in which a very trivial idea was introduced, something that goes back to the Greeks, the oblique rotator, that the magnetic field was variable. Actually, what Deutsch found was that the star HD 125248, it's a chemically peculiar star. And it's one for which Babcock had measured a magnetic field by the technique we've talked about, by Zeeman effect. But what Deutsch found was something unexpected, that the field was varying periodically, not periodically on times of decades, but days. And with that, cleverly and obviously, he came up with the idea that what you were seeing was a magnetic field that was inclined but frozen onto the surface of the star. In other words, a magnetic field like the Earth, an inclined field, hence an oblique rotator. That was the beginning of a whole industry. But it was an industry of very few people because first few could measure the magnetic fields. That is, it requires fairly high resolution. And it also requires persistence. You've got to follow this long enough to be able to measure that the field is actually periodic. So by the 1970s, we had a very clear idea that a class of magnetic stars, the chemically peculiar stars among the A stars, which are between about 1.5 and say 3 solar masses, their main sequence stars that have anomalously strong lines of the metals. So they had already been noted at the beginning of the 20th century. Alpha Tucanus Venaticorum is the most famous example. Beta Corona Borealis is another. So I'll just say, while you're waiting for a T-core board to do whatever it won't do, you might want to take a look at Beta Core, which is much brighter and some might say more interesting. But among the HR catalog, among the Bright Star catalog members, there's a surprising number, like 10% of the A stars have some metal peculiarity. And it turns out that many of those fit this oblique rotator model, that there's a difference. Now let me make this clear. There is a difference between the magnetic fields on these stars and sunspots. and flare stars. That is, stars like the sun do not have large-scale, permanent, oblique, or aligned magnetic fields. Stars in the A star range and the B star range, and now it's clear even O stars, so magnetic fields extending to 30 or more solar masses. Those are stable, or at any rate stationary, that the field configuration does not change over thousands of rotations, where on the sun, the spots don't even last one rotation. The average time scale is only weeks for one to appear and then disappear. So something is fundamentally different between these in the generation of the field in the first place, that one of those requires active regeneration, in other words, an active dynamo, and the other allows you to sort of freeze some configuration in. And if you think about it, planets are somewhere in between, because the Earth does have an active dynamo that flips. Otherwise, the fundamental tool for understanding plate tectonics would be lost. The fact that the field actually changes sign and does so randomly. It's not anywhere near the clock that the sun is. And then there's the other, which is not just that there are the AP stars and the chemically peculiar stars on the main sequence. We'll come back to what Francois was talking about, the AM Hercules stars and magnetic fields on accreting white dwarfs and neutron stars. Those fields do not change over time. So the mapping of those fields, specifically the ones that are connected with neutron stars, requires a different technique than what you would have for sunspots, and a different one than you would have for normal spectra. Okay, so far?
Yeah.
Now let's go back to that picture of the sun. Back to the surface. So it isn't simply that here we have this filamented magnetic field. Remember, the image that you saw from the carbon-4 was simply showing that this whole region had magnetic confined material, heated material all through it. It's that when we're looking at this, and when you also looked at the other aspect of the field, namely that the rest of the star was also showing that where the field is strong, it's dark. Dark means it's radiative. See, the reason the sun is so uniform in its surface is that it's convecting, that there's the granulation, okay? Those wonderful images that look like either bowls of rice or uh, a bee's nest. The structure of the surface is fragmented into these rising and falling elements of gas that are either warm or cold, and so they're either bright or dark. Okay, the entire envelope is not convective, but there is this motion at the surface because of the requirements of opacity and the transport of energy from the interior. The thing that's striking about the field is that something about the presence of the field causes the region to be dark. This is exactly the same as saying something is cooling it, or that the energy is not being efficiently radiated, or that something is transporting energy in a non-radiative form. Okay? Otherwise, if you suppress the convection, it doesn't get as hot. And so it's not as bright, and therefore, relative to the rest of the photosphere, it looks dark. And the evidence that you have from the corona and the chromosphere is that in the regions above the active sites, where the magnetic field is concentrated, the corona is hotter, the plasma is heated, but at the photosphere, it's just the opposite. Something is suppressing the convection. This is one of the fundamental problems in solar physics, and ultimately one of the fundamentals in stellar physics. If you make this extreme enough that instead of these spots occupying a couple of percent, they occupy most of the surface, then you would have a flare star. And if you're somewhere in between in a binary system, you would have an ARAS star. The most active stars can have fields that can completely change the envelope structure. So it isn't simply that you're seeing flares. It isn't simply that you're seeing the effect of creating or dissipating magnetic fields. There's a whole reaction of the whole atmosphere of the star to whatever happens in that magnetic field structure, exactly the way the film showed, that you get a heating of the corona above the active region, which is strange if you think about it, because you've suppressed the vertical and horizontal motions. That's one of the things we don't understand. And that's also one of the main problems in understanding solar physics. You see, the other thing is when you look at this, something is very clear. This ain't no dipole. These individual regions are very strongly concentrated and they dissipate. They're fibrous and fibrils. You have bridges that are formed within these active regions. You saw those in the film that showed the coronal structure. There are arcs that connect from one of these bipolar regions to another. And the surface field is tied to the material of the convection zone. So you can imagine this as being the equivalent of pasta, specifically a very, very thin spaghetti inside some kind of boiling medium. And here I'm not just being facetious in the comparison because I'm in Pisa. It's that pasta serves many purposes, one of which is to understand magnetic fields, that the field is frozen into the water or into the convection zone in the way that the pasta is being transported by the fluid, which means it twists, it knots, it concentrates in some regions and spreads out in others. And obviously, you've seen this where you get the threads concentrating, you don't get vigorous convection, and where you have the threads spreading out, that is the spaghetti in fibrils throughout the fluid, then it can be turning over vigorously. And it's the same thing here. The only difference being that this doesn't, you don't get flares in the kitchen, I hope. But we can understand it in the same way that deep in the interior of the sun, there is something like a global magnetic field, a reservoir of fluid that's magnetized. If this gets twisted and concentrated, the field has a different density than the gas. It contributes to the pressure. So taking a field and twisting it and knotting it increases the energy density without changing the matter density. It makes, on the average, for a kind of light pasta, it's almost a ravioli or a fusilli, that it's hollowed out, and consequently it's more buoyant. The argument is that in this lower part of the convection zone, you have a twisting up of the dynamo because of the differential motion in the interior of the sun. Now, I realize this, said in words, this is actually rather, excuse me, rather too complicated. Perhaps I can give you an example by using this wire. So you can imagine that the magnetic field is dragged rather by the rotating part of the sun. That in the interior, if we had a field line that stretched from north to south, that because the sun is differentially rotating, differently at the pole than the equator, this gets stretched out, twisted around, and comes out eventually like this. And because it can be twisted and knotted by motion of the convection, this can pop up through the surface, suppress the convection in these regions, and give you arcs here that constrain the plasma. And that's what we see in the solar corona and the solar chromosphere.
Steve,
Yes.
I've just got a quick question.
Please.
Can magnetic reconnection happen in the interior of the sun?
Oh, definitely.
Oh,
It's
okay.
just we don't care.
Hmm.
No, in fact, I'm being facetious. Magnetic fields, when you have currents in opposite directions, will be connecting on all scales. In fact, it's the reconnection that's absolutely essential for the dynamo. We don't treat it in detail. This is the main difference. The reconnection, when you talk, reconnection means that you have field lines that are in opposite directions. And so when you bring them together, they annihilate. And it's the equivalent of saying you take a northern and a southern directed field. So I'll do it like this. And when you bring them together, this creates a loop in this direction, and this creates a loop in the opposite direction, and they blow apart. What you're doing is, in effect, changing the configuration and tapping into the energy because you have currents. Okay? Now, this happens on all scales. If it's ideal in our models, now this is different than reality, of course, we can say, well, suppose we just forget about that. That's the equivalent to saying the medium has no resistivity. If it has any resistance at all, if it is dissipative at all, it's reconnecting. So the growth and decay of the field essentially, not slightly, essentially depends on the presence of a resistivity. And that is the same thing that drives reconnection. The physical process that accelerates the particles, that gives you the flares, that energizes the gas, that's a different issue. That does not happen in the interior because you don't have the low densities required to get the particles to actually accelerate. So in other words, the resistivity is there, but you have no net electric fields that can build up locally that can generate a sufficient energy to give you those high energy particles when that same process happens in the outer part of the atmosphere where the density is low. then for a short time, you can actually get you can get an electric field formed. Now, you know examples of this in the Earth's atmosphere, that in the surface, you don't build up charge, but in the atmosphere, you can. So when you get a lightning discharge, the charge buildup is actually in the cloud. It's that it's generating a net charge difference because you actually have charge separation because the densities are low enough. You would never get those in the surface itself. You have to induce it. Okay? So in the interior, you are getting the reconnection, but you're not getting the effect of the additional effect of anything but heating. It's not going into non-thermal. It's just going into hot. Um, the deeper you go, the closer you come to an ideal situation. That is when the temperatures get high enough. And at that point, no, you don't get reconnection. Not, except when you have large scale currents. So it's the same as taking two vortices. You see this in accretion disks, that when you have vortex structures, they can be magnetized and they can merge. So it's not really the same thing as reconnection in the sense that we normally think of, like like the things that generate um, intense auroral activity at the boundaries of magnetospheres. You'd never be able to see that dynamically from spectra. The way you tell that that's present is by the heating that's created, like the heating in a flare star. And the reason you see the sudden increase in emission of, say, H alpha or of the calcium lines is that locally you've dumped a huge amount of energy into this background without necessarily without accelerating particles. You just heated it. And the emission is then from a region that's been heated that's slowly cooling by collisions and recombination, where in the corona, when this occurs, you can see it in radio because you've accelerated particles you've accelerated electrons to relativistic energies in magnetic fields that will then cause synchrotron radiation or gyromagnetic radiation. But otherwise, you would not. Otherwise, you wouldn't be able to tell that spectroscopically. You don't see reconnection events directly. They happen on too small a scale. You see the effect of the heating. And the other problem is that the only way you're going to see the actual reconnection is at very high energy, like the flare that you were seeing. That's not just high resolution spatially, but it's also very, very specific energy regime. In the case of the strongest flares, you're going to have to use X-rays or gamma rays to actually probe the site. That by the time you're seeing things in H alpha or calcium, it's over such a large region that you've learned virtually nothing about the actual site in which the event occurred. I hope that wasn't too confusing.
Oh, thanks.
You see, all of these are connected. That wherever there's a field, no, let me say it differently. Where there's a wind, if there's a field, there is a corona or an outflow like you see in the corona. Why I'm mentioning that is that we spent a lot of time in earlier discussions on the outflow from stellar winds like massive stars and novae and supernovae. and somehow I never used the words magnetic field. That was a mistake. We don't know, except that is, we don't know the details, but we do know that the magnetic fields not only exist in massive stars, but it also can control their winds. The way you know that is stars rotate. And from the ultraviolet lines that are formed in the photosphere and in the wind, you can see if they're periodically variable. And in fact, some of them are. So it appears that magnetic fields can be generated by and present in stars virtually over the whole mass range. They aren't avoidable, in other words. They may not dominate the structure, but they certainly play a role in what you're going to observe. The strongest magnetic fields that we know on stars on the main sequence are of order tens of kilogauss. To put that in perspective, the mean field of the sun is about a Gauss. The typical field in a sunspot is a few kilogauss. And the fact that you have a star whose measured Zeeman measured magnetic field, Babcock's star, is over 30 kilogauss, and this is the average field over the whole surface, should tell you that there's something going on here that's interesting, because that star has a structure of its atmosphere that must be dominated at some level in the atmosphere by the magnetic field. And yet we don't know what effect that has on the spectrum. The only thing we know is that the spectrum changes as the star rotates. So when we're looking at sunspots, if you take an average over this surface, and this is now getting to the technical side of what you would see as observers, if you're averaging over this whole surface, which means you can't distinguish individual regions even by rotation if it's slow enough, you have to think about this as a problem, just physically. When we look at the sun, we learn in our childhood that the sun is a G25 star. Okay? Remember? And Vega is an A05, hence main sequence star, and spectral classification is something based on integrated spectra of stellar surfaces. Okay, we're agreed on that? That is a G25 star. Let that sink in, please. That surface is not uniform temperature. And that surface's temperature changes over time, because the different regions that are either strong or weak are going to be either hotter or cooler. Lines that are formed from ions are going to be weighted differently than lines that are formed from neutrals. And so when we talk about a stellar spectrum, what we mean is really something that is so averaged over this surface that we must consider that it is only a mean quantification. There's the demonstration. This is a single rotation sequence, 14 days.
Wow.
And this is just the photosphere. Never mind the chromosphere. Never mind the emission lines. You see what's coming into view? this region is going to be a dark spot. That means its temperature is lower. And if the temperature is low enough, it's going to have molecules, and this region won't. Okay? It happens that with most stars, like the sun, all of this gets beautifully averaged out. These regions are, no matter how large they appear to be to us, they're really very small overall. A few percent of the surface really doesn't make that much of a difference. But if we talk about determining the abundances of the elements, remember that to do that, you have to solve the problem of the formation of the lines. If the surface isn't uniform, you can't ignore the variation from one region to another. It becomes a problem that we are only now, as a field, able to face because of the computational difficulties. But one of the things that was noted already at the beginning of this millennium is that the difference in the temperature actually does foul up the determination of the abundances. And that's the other reason I'm mentioning magnetic fields. In the regions that have weak fields, the lines are not broadened. I hope you'll accept that. Not because they're cool or they're suppressed. It's simply, if the field is weak, the line is whatever the line would be with no field. Okay? But if the magnetic field increases and the lines split, then now you've taken the total absorption and halved it or decreased it. The result is that the line may have been saturated at the beginning, and it's desaturated by being split. So when you determine the abundance, you get a different answer. The line looks weaker than it did. And because you've changed the opacity, it also changes where in the atmosphere it's formed. So when you're looking at the center of the disk, it's not the same as when you're looking at the limb. You already know that for stars, that the boundaries of stars in the optical are from the upper atmosphere, and so they're darker. And in the center, you look deeper than you see at the edge. Well, here it's even worse, because if you have an active region on this boundary, it may be excessively dark. Or if you have an active region in the center and no active region, you may have the same brightness on the boundary as you have in the center. And all of that changes over time. It's not to say that we can't work with this. It's that one must be aware that this is what stars really look like. I'll go back to something from, again, from the 50s, when an exchange occurred between, sorry, in the 60s, when an exchange occurred between Hoyle and Taylor, where Hoyle had quoted Eddington about, "One day we shall understand something so simple as a star." Sorry, maybe someday we shall understand something so simple as a star, which is what he wrote actually a century ago, at the end of The Internal Constitution of the Stars. And Taylor rejoined, "From 10 parsecs away, you'd look pretty simple too, Fred." So it's the same thing here. From 10 parsecs away, the sun looks uniform. But we must be aware that this is what all stars are going to look like at one level or another, because of the action of the dynamo in the interior. ordinary stars on the main sequence that do not have strong fields, where the field is not so strong that it actually structures the envelope, but it's being regenerated and being reconnected and being again regenerated. This is what the surface is actually going to look like. So when we talk about the surface of a star, again, we are averaging over all of this. Okay? So again, I hope that, okay, so okay, so now let's see. Okay, so the technique for recovering the structure of the field I do not understand here why this is always doing what it shouldn't be doing. Fine. This is the result of Doppler imaging of a star. In this case, Alpha Toucan Van, which is the prototype oblique rotator. This is the phase, and this is what you get from mapping the field with different different transitions. It's just to give you an idea that one can actually begin recovering the surface. But in this case, it's because of these very large inhomogeneities. Now, this is why I was also adding that one of the things that must happen is that because of the field structure, the atmospheres are not uniform. The way that this technique, this Doppler imaging technique works, is very much like Doppler imaging of an accretion disk. There's an underlying assumption. In this case, that the only thing you're doing is painting the surface. And that the effect that you have on the line formation is no more than changing the projected field on the line of sight, that there is no change in the physical structure of the atmosphere. The reason I showed you the solar images is to emphasize just the opposite, that the magnetic field does change the structure of the atmosphere. And if it's changing the density and the pressure, it's going to change the spectrum. So one should be very careful about over-interpreting this kind of reconstruction without understanding the underlying physics, that this surface of this star is very clearly that connected with the magnetic field. You can measure the overall field by Zeeman effect, and you can see that the individual transitions show lines that are moving. Now, this is the other point I wanted to make. There's some point where you may see both poles. That is, one of these is, in this case, you're looking this way. One of these is going to move toward you. The other one is going to move away from you, obviously. But at this moment, the field is zero that you measure because there's no pole pointed toward you. As soon as this moves, the positive pole now has a negative radial velocity. The negative pole has a positive radial velocity. And at this point, where the field is maximum, the radial velocity is zero. There's some point then in the variation of the lines where they cross over each other, where the combination of the radial velocity and the direction of the field causes the components to shift. That's the proof that there really is a global field. It's called the crossover effect. That is what goes into this model. You can see that in the base, where here the direction of the magnetic field is shown. This maps the relative contribution from the line in different parts of the surface, and this is the projection of the field in that particular line of sight, measured using this Doppler imaging technique. To get this to work, you have to assume that the surface, unlike the sun, is rigidly rotating, which means you have to observe this for long periods of time. The longest periods we know for rotation are actually years for stars that are magnetic. For those that are in binary systems, where we know the field is being regenerated, stars like the ARAS Canvan stars, or the DMEs that are in binaries, the dynamo is acting more strongly precisely because the star is in a binary. A star, the sun and stars like the sun with that age rotate with periods of about a month or a few weeks. There are ARAS Canvan stars, there are binary systems, and actually Algol is even one of these. Systems that have star spots. And we know they have spots because they show that in their light curve. I'll show that in a moment. But they have periods of days, which means you have this rotation, this winding up effect, much amplified simply because the star is in a binary and it's been constrained to rotate as a faster system. The observation that this is actually connected directly with the light curve is, I hope you can see this, that there are light curves here marked ARAS Canvan. Yes? No?
Yes, yes.
Okay, so thanks. So this is simple photometry. Precisely the thing that I make insulting remarks about. But this is very important because this is an eclipsing binary. RS Canum Venaticorum is one of the prototypical stars with active chromospheres. It was discovered already in the 1960s and understood to be star spots in the 1970s by Rodinot and Hall and Strassmayer. The thing that you'll notice is it's an eclipsing binary. That's one of the great advantages. It's a period that's about 5 days, and the stars are evolved stars. It's not main sequence, but they're not mass exchanging. So this is not an accretion disk. If you looked at this as a cataclysmic, you would say, oh dear, this is an SU Cam star, SU Ursa Majoris. So we have here, we have a super hump or something in it. It's not a disk. It's actually that there's a spot or an active region that's present and then not present. And the eclipses aren't changing. It's the surface that's changing, and it's migrating through the light curve. That its minimum here is its secondary, and then it moves toward primary, and then it goes away. To get this kind of change, this is 0.3 magnitudes. Okay? to get this kind of change requires that you have something like a third of the surface covered with a region that has a different temperature. Now think about what this is going to do to the spectrum. So you have a star whose surface not only has different brightnesses, but physically different spectra. That the region which is the spot has a temperature that may be 1,000 degrees lower than the rest of the photosphere. In this temperature range, and this is roughly solar type, one of those is going to show molecular lines, and the other one is going to show ionized metallic lines, and they're going to be in the same spectrum. And it's not because you have two different stars. It's one star with two different regions. This is the way we look for the magnetic fields. These light curves are absurdly primitive. This is just V-band photometry in the days of ordinary single photoelectric photomultiplier observations. Now we have TESS and Kepler, and instead of a few of these, we have thousands. And they do show cycles, and they are very complicated. And now we can finally begin looking over time at the evolution of these dynamos and these fields. And that's why I wanted to bring this up, because having this sample to work with, we can finally perhaps begin understanding this magnetic field generation mechanism. We also know that there must be a connection between the fields that we see in the cataclysmics and on white dwarfs, where the fields can reach a couple of megagauss. Okay, for pulsars, we're in the teragauss or higher range. Typical magnetic field on a pulsar is something like 10 to the 12 Gauss. We'll leave that aside. That is truly nature being obscene. But when we get to the magnetic fields on white dwarfs, they're considerable, but they're not so large that the energy density in the field is a major fraction of that of the whole star. So that's what's different with a neutron star. Where the hell did those fields come from is a major question. We know they're there because of everything that we've talked about. They dominate the inner portion of the accretion disks when they occur, but not every white dwarf is magnetic. In fact, only a small fraction of them are. Not every cataclysmic shows the effects of a magnetic field. Some do, some are accreting, some aren't. But those fields came from somewhere. They were in a star at some point. They were frozen in. The fields we see on the white dwarfs and the neutron stars are not changing in time. So these are the same kinds of stable structures that I was talking about for the main sequence chemically peculiar stars. They're not active dynamos. What caused them? Where did they come from? We don't know. So the observations of the variation induced by the field, being able to map their structures, is going to be the clue that will tell us about their origins. If we have a simple dipole field, that puts a constraint on the originating flows and current distributions. If we have something that's really complicated, like we see on the solar images I was showing you, it's a different issue. We know that a white dwarf was once the core of a star, so what we're seeing in the field must be a relic of what happened in the earlier stages of that star's life. to make life even worse, if that is what this core of a star looks like, if the white dwarf is the product of that core, what happens in a supernova when we have a core collapse? Or if we take an accreting white dwarf and it has a strong magnetic field, as it's accreting, if we drive it over the critical mass so it collapses, what happens? The magnetic field must be amplified if it collapses. How does this control the explosion? We don't know. We're just beginning now to include these. And that's why I'm bringing all of this up. This winds up forcing us to face the greatest uncertainty we have in astrophysics, how to couple electromagnetism in this large-scale fluid mode with the fluid motions and energy generation and energy loss mechanisms that dominate astrophysical objects. We cannot ignore these unless we have evidence that we can. And that's where the spectroscopy comes in. That at least at the level of stars on the main sequence, or even in giants, we can constrain the role of the fields by what you're seeing on the screen, by looking at the spectra and the photometry. Okay?
Yes.
The other role, that is how fields originate at all in stars, connects everything I've just been talking about with one other class of objects. Look at these light curves, and instead of thinking of these as post-main sequence, think pre-main sequence, because this is what a proto-binary is going to look like. That it, as long as you have deep convective envelopes, as long as you have dynamos, and remember that young stars in formation are rapid rotators, you would expect that T Tauri stars and young protostellar objects are going to have strong dynamo fields. And so they're going to show flares and they're going to show star spots. And their interpretation is going to be connected with strong coronae and with strong environmental heating, potentially even the heating that drives winds. So by studying the ARAS stars and by studying dynamos, we can also understand something deep, both literally and figuratively, about the structure of protostars. And that allows us to go further back toward where the seed fields come from, which is the magnetic field of the galaxy. And that's the last thing I wanted to mention as trying the last piece of your patience, namely that the other thing that we have in this picture is that the magnetic field is here. So I need to change the screen one more time. Here. The magnetic field of the galaxy can be determined because we have electrons that are cosmic rays that have been accelerated by supernovae and by flares and by all of these other processes that are already themselves connected with magnetic fields. And so if we look at the synchrotron emission from the galaxy, this is what we see. This is a map of the galactic magnetic field. along the line of sight. It's only one component of the field, but this is obtained by taking the equivalent of the difference between right and left circular polarizations. It's a radio measurement. In fact, this is from the Planck satellite. The thing that's important is you see that there is a magnetic field of the galaxy. If I wanted to pull pull a joke on you, I would say, oh, this is actually Alpha Tucanvan. Okay? In other words, the field of the galaxy looks remarkably like the field of the sun, except we're dealing with something here where the scale of these fields are kiloparsecs, not kilometers. And yet there's something here that looks very much like a dynamo on a very different time scale, on a massively different spatial scale. But if we understand the sun and the stars using spectroscopy and the mapping of the field, we have a chance that we're also going to be able to understand something on the scale of galaxies. This is not the polarization of starlight. This is the polarization mapped directly on the magnetic field lines from the synchrotron emission from the electrons. So this is actually the direct measure, not the indirect measure of the field. You don't need sources behind you to see this. So that's what I wanted to end on, just to point out that also here, this is the plane of the galaxy. So these, here it comes, these are loops. These are arcs. The galactic center is here. And there are arcs here that are on scales of hundreds to kiloparsecs, and small scale structure as small as a few parsecs. Supernova remnants that create additional arcs, super bubbles, molecular clouds, all of that on a scale that shows the dynamo or a dynamo type process must be acting here. This can't be just frozen in. Okay? I wanted to end on this just to give you a feel for how one can then extend the arguments that we've been using, starting from the very small scale and going almost to cosmic. So I really should stop torturing all of you and just say thanks. Any questions or comments for now?
Yes, maybe Steve, um, if you could come back on the fact that depending on your point of view with respect to the magnetic field, we don't see the same thing with the Zeeman effect. When we look parallel or transversal to the field, we don't see exactly the same thing. Could you explain this a little bit more, please?
It really has to do with the way the lines are split. That the radiation that's emitted when you're looking down the field means that you're looking at the projection of the magnetic moment of the system along the field. When you're looking transversely, you're looking at a different projection of the magnetic moment. So in looking along the field, it's the same atom. It's simply that the radiation pattern that you're seeing is different. It's not an exact analog. but you know that when you're looking at the daytime sky, depending on the angle you're looking at, you see different brightness. That is the angle relative to the sun. It's
Mhm.
it's exactly the same process. You're simply sampling different lines of sight. So here it's the fact that when you're seeing emission or absorption, there's there's a pattern, an angular pattern to the response function. So when you're looking this way, you're seeing one part of that pattern. When you're looking transversely, you're seeing another. If that is less than satisfactory, then the other example would be, although this is classical, that when you have a dipole antenna, like
Mhm.
when you do something primitive, like instead of putting a dish, you put a Yagi on your roof, okay? The pattern that that forms is an emission or absorption pattern for that that array of dipoles. Okay? And so it makes a
Mhm.
difference if the radiation's incident this way or this way.
Oh. Okay.
Okay? You can think of the atom as a resonator that is responding to a particular ensemble of frequencies. Now, I don't mean that as orbits. Okay? The usual way that people explain this is to go back to something as primitive as the Bohr atom and say, well, you've got the electrons going like this in their orbits. And if you have a circular polarization, then it causes an oscillation, and that's why you get this effect. Forget it. That's electrons in a magnetic field. That's not electrons in an atom. Okay?
Mhm.
The fuzz ball that is the atom is the antenna. So when you're looking in different directions, you're actually looking at different beams. And I think that's the easiest way to see this. It's that the response of that system, like the separation of the components of the antenna, depends on the magnetic field.
Okay. So it means that photons are not emitted isotropically.
Yes, they are not.
Okay.
They're not. And that's why we talk about dipole radiation or quadrupole radiation. You know, when we talk about forbidden lines, you have electric dipole, which is permitted. You have magnetic dipole, which is prohibited. It's a forbidden line. And you have electric quadrupole, which is also so-called forbidden. That is, the permitted lines have a very strong, essentially dipole pattern, and the quadrupole have intrinsically weaker and a more uniform pattern. Yes, every transition, when you talk about the states having angular momentum, that is when you write down a spectroscopic designation, that is telling you an angular pattern for the re-emission and for the absorption. Yes, very much so. And this is also why you have different scattering functions for different molecules and different atoms, depending on the state. And this actually, to put it really bluntly, this is why when you're measuring symbiotic stars and looking at the Raman features, why you get a phase dependence in the Raman line, because you're scattering off of a dipole. That is, the oxygen 6 line in the UV is scattering off of the Lyman beta line, which is a permitted line. It's a dipole. So as the system rotates, you get a polarization. and that polarization is that of a dipole. Okay? Same thing as
Okay, yes. Thank you.
okay, so others? One of the most difficult areas in astrophysics seems to be radiative transfer. There are whole generations that don't think this way anymore. But where life gets really interesting is when you ask what happens when you have radiative transfer in media that have these other effects, like magnetic fields, that you can actually recover the structure of the gas remotely by looking at how different lines form depending on where they are in the field. I think that's actually quite remarkable, that we can map out the surface of a star because it's magnetic. I think that's remarkable. And that we can understand something about the generation from the dynamo empirically where we still have no clue theoretically. I mean, the last comment I'll make is this is really the frontier. Just as we don't know how stars form in detail, we know magnetic fields are involved. Otherwise, we would not see Herbig-Auro objects. We wouldn't see jets. We know magnetic fields are involved in accretion disks. Otherwise, we wouldn't see accretion. Magnetic fields are essential to creating the viscosity that drives the accretion. We know that the fields are present on scales of active galactic nuclei. Otherwise, we wouldn't see radio jets. We know that there are fields present in clusters of galaxies because we see radio lobes on quasars on scales of hundreds of kiloparsecs. And that means that plasma is floating around in the medium that's dominated by dark matter, but otherwise confined, and so eventually could very easily be incorporated into the formation of the galaxy. Okay? That's why this is important. This is as universal a phenomenon as gravity, and far more difficult. So I'll stop there. And I think next time the promise was AGNs, and I will definitely connect
Yes.
AGNs with magnetic fields. I promise.
Very soon. Thank you very much, Steve.
So I should stop the recording now or what? I don't even know how to.
I do it.
Good.